Yeah, basically saying, let's go get SDSC for Kevin. Actually, this is a machine that lives on SDSC's network, but it's actually managed by Tsutomu Shimomura. So he gives us his logs to look at, and it's a useful way to find people probing things. So there's a lot of different syslog messages and a lot of noise. There's a ton of stuff: nominal status message, redundant information, and some messages that don't actually even say anything useful at all. So we collect several million lines of messages per day, and the small and maybe interesting ones are going to be missed. Even the large and interesting ones might be missed if we don't know they exist. So I think data mining can help me find patterns of activity that could be interesting. Maybe they won't be interesting, but then at least they're nominal status information. Groups of message, looking at message frequencies, things like that, that could be something worth investigating, and so on. And CERT has this wonderful quote in one of their documents. It says, look for anything that appears out of the ordinary. But how do you know what's out of the ordinary until you know what's ordinary? So anomaly detection is actually the most common thing that's prescribed. Just about everything you read about logging, including stuff I've written, says go look for the weird stuff. Go look for something unusual. But it requires normal activity to be identified, along with things like thresholding and windowing. If you want to look at user logins that are outside of a normal period of time, you have to know what the normal periods of time are, and that sort of thing. So data mining can do this stuff for us, but data mining requires your information to be formatted, to be defined. Data mining is basically an application of statistical analysis, at least the data mining that I'm looking at. So you need to know, data mining tools need to know what the input is. So things like databases, XML formatted data, processing counting files, things like that are relatively easy. Network data are relatively easy to use data mining techniques on because we know the format. But syslog data isn't clearly defined. There's no data dictionary or anything to work with. There isn't even a standard language for it. A few examples of syslog messages, just to give an idea of what we're looking at. Syslog messages have what I call a header and a body. The header is a relatively regular format. Timestamp, hostname, what I call a service name or the process that generated the message, and a process ID. This information is generated by the Syslog API or the Syslog server and so on. And then the body of the message is the rest of the message. These are 3 different message bodies, just to show some of the differences. This is basically arbitrary text. Even though this is where the real interesting information comes from. This is arbitrary text written by the programmer that writes the application. And as Larry Wall, who wrote Perl, once said, the 3 virtues of a programmer are laziness, impatience, and hubris. So what Marcus Random once said was, programmers should not be allowed to write log messages. And basically, programmers write what they want. They often write this stuff, or usually write a lot of this stuff for diagnostic purposes while debugging their own code. The syslog protocol, the syslog environment itself, was actually put together by Eric Ullman. And he actually said the only reason he did it was to get the printf statements out of his code. So we've got this tool that wasn't even actually written for what we're using it for, but everyone uses it. And everyone uses it differently. And the people who are using it are thinking about how other people are going to use it. And what's the fun in writing, in going back and cleaning up your log messages and making sure they're formatted, make sure they're easily parsable, writing descriptions for them. That's the laziness and impatience part. So for example with this, I decided to just work through and write code that will parse out the header information of messages. So I could separate things by service. So I could at least group things by the service and maybe look at some of the patterns that existed. So this took me actually several days of writing regular expressions to match headers, and identified 23 different header formats in 1 week's worth of our Syslog data. Some of them don't have a host name, some of them do, some of them don't have a service name, some of them don't have the process ID, some of them have additional information. This message was forwarded by this host, things like that. That alone was a pain. Coming up with ways to parse the actual text is much harder. And this is why I think, as far as I know, there's very little work that's been done on data mining of Syslog data. I've come across a number of papers on data mining for security, but they've all worked with things like a network or system call traces. And I'm pretty sure it's because the data was easy to work with, it was clearly defined and that sort of thing. If people stopped to look at Syslog, they would get so caught up in trying to extract the data that they never actually get to do their data mining, which is kind of where I'm getting to. So there's also lots of tools that call themselves log analysis tools, things like Swatch and LogSurf and so on, but they're actually just log parsing tools. What they expect as input is a description of the log messages you want to work with. So you have to know what you're looking for in the logs in order to work with those tools in any useful way. So to get to my actual goal, which is data mining of Syslog, I need to develop a catalog of messages, a way I can uniquely sort out messages based on what I'm calling a message type. Now I'm going on the assumption that any given Syslog message, and also in my experience, contains some hopefully descriptive text and optionally some data. As an example, here's a simple message that has some connection refused from, and the data portion is the IP address in it. What I want to do with the message type is be able to identify like messages. So another example, whoops. I lost one of my examples. Well, what my example was is here's a connection refused from one IP address, another message is a connection refused from a different IP address. I would consider to be the same message. Okay, so that would be a different message that would not be matched with that message, and so on. I'm defining the messages, or I'm thinking about messages as a collection of variant and invariant text. So what I think I want is a set of templates or patterns that are used to match messages which identify the variant and in-portion variants of the message. Now, patterns need to be good enough. There are obvious, my slide got out of order. There's the like messages, there's the unlike messages. So this is what I'm thinking maybe a template looks like. Okay, where %s is a string. Could be %string, could be %i for IP address, or something like that. There are obviously trivial patterns that will match messages but really aren't useful for anything. So patterns need to be good enough or best match to actually be useful. So I've identified some properties of message types and their patterns. Some simple properties. If you have a set of patterns to match against, any message should match just one pattern. If a message matches 2 or 3 patterns, your patterns aren't good enough, or something else is wrong. But a pattern can and should match multiple messages. If a pattern matches only one message, it's probably too good, or something like that. For instance, if my pattern here had the IP address in it, it would match that message, but it would match only that message and not be very useful, and would not be identifying the invariant portion of the data. So in addition to that, the service type of the message goes along with the message type, because you can have two, you might have